Okay, let's finish this up with problem 5. We have this crate hanging from the end of a rope with a given length, which is of course L, and we want to push horizontally on the crate with varying force to move it 4 meters to the side. Okay, so the first question they have is when we are, after we move it 4 meters to the side, what is the final force here on the crate? This final horizontal force F here on the crate that's holding it in place. So, very simple question to ask is what are the forces acting on the crate? We've got our applied force F here, and then we've got the weight of the crate, and we've got the tension on the rope. So, what this is, yeah, it's a free body diagram. One of those problems. So let's do a fast little FBD on the crate. Actually, what we want to know is this angle theta here. And the key to finding theta, that angle, is to remember that the rope does not extend. So let me do something a little better there. There we go. So this length here is still L. Okay, this is L when it's hanging straight down. It's still L when it's hanging straight down. And then this here is 4 meters. I'm going to call this D, but I'm just going to say, just so I can do it symbolically, D equals 4 meters, L equals 11 meters for me. Okay, so theta actually is the arc sine, or, well, really, sine -1 of D over L. Okay, so there we go. Now we've got our little FBD for the crate. So let's do that, FBD crate. And yeah, good old free body diagrams. Let's do this. Let's draw the tension in the rope like that at an angle theta from vertical. We've got the force, the applied force there, and we've got mg going down. So let's do, and of course I'm going to do my x and y like that. Okay, so the standard old x, y. And our component FBD for the crate is going to look like this. This is going to be tension cosine theta, and this is going to be tension sine theta, and then this is going to be mg, and this is going to be F. So sum of forces, remember it's motionless at the end, so it's not accelerating, so all these things have to balance out. So sum of forces in the y direction equals 0, which means t cosine theta minus mg must equal 0, which means, of course, t equals mg over cosine theta. And then the sum of forces in the x direction has to be equal to 0, right? Equals 0, and that means F, which is our applied force, minus t sine theta equals 0, which means F equals t sine theta, and t we found was mg over cosine theta, so F equals, let's see, right, mg sine theta over cosine theta, or more simply, F equals mg tangent of theta. Okay, so let's find out what this is for us. Theta is the arctan of theta equals the arc sine of d divided by L. That was 4 divided by 11 for my numbers. Okay, so there's our theta, and then I'm going to do a mg times tangent of that. So what was m here? Let's see. M times g times tangent of that. Okay, so the mass was 220 kilograms, so I'm going to do 220 kilograms times 9.81 mg times the tangent of what we just found, and that should give us, if I'm not incorrect, the force acting on the crate. So that should be 842.4, so 842 newtons. Let's see if I've got that right. Oh, we're going to just do number 5, right? 5, yes, 842 newtons. I got that one right. Yay for me. Okay, during the crate's displacement, what is the total work done on it? Now, this is one of those sort of tricky, well, sort of a trick question. So the thing is that it starts with 0 kinetic energy, right? It starts at rest, and then it ends at rest, and so it goes to the final position, then it ends at rest. So what's the total work done on it? Well, the total work done on it is going to be the total change in kinetic energy, right, for the crate. So it starts with 0 kinetic energy, right? Because it's at rest. And at the end, it also has 0 kinetic energy. So what's the total work done? If it has a change in kinetic energy of 0, the total work done is also 0. Really, it's that simple. Kind of silly, I think, but for them to ask it that way, but there you go. See, there's the answer. Okay, so let's move on and do part C. During the crate's displacement, let me move this down a little so we can see the whole thing. There we go. Okay. During the crate's displacement, what is the work done by the weight of the crate? So now we actually have to find something else, something out. So let's find the crate's displacement first. Let's see, displacement starts here, okay, at this blue dot I've just drawn, and goes up to here. And this is our displacement, which I'm going to call delta R. Okay, so what is delta R? Well, delta R equals, and it goes 4 meters horizontally, remember? So 4 I hat meters. I'm going to leave the units off for a minute. And how many meters does it go vertically? Well, it goes up. So it starts off hanging 11 meters down from this thing, but then when it moves up, or when it moves to the right, it shifts up a bit because the length of this rope stays 11 meters. So the vertical distance down from this rope is actually going to be 11 times cosine of theta. So I'm just going to go ahead and see what 11 times the cosine of that answer we found before, which was 21.32. Okay, so that's where it ends at. But remember, it starts at it moves. That's how this here is how this 10.24 is how far down it is from this anchor point here at the end, 10.25 meters. But it actually starts off 11 down. So really, it comes up from negative. Well, let's see. What I'm going to do is I'm going to say it starts at negative 11 meters in the vertical coordinate. So it starts at negative 11 meters. It comes up to negative 10.24. So minus. So actually, it's going to start at, oh boy, negative. That is our final. So actually, okay, negative that is our final. Okay, minus negative 11. And this is all convoluted, but what it tells us then is we go up 0.753 meters. So 4 I hat plus 0.753 j hat meters is our displacement delta R. Okay, so now what is the force acting on this thing? And I should point out here that what I'm doing is, remember, we can find the work done by a force. If the force is constant, we can simply F dotted with delta R. Okay, so if we know the force, we can express the force due to gravity as a vector, and we express delta R as a vector. We can just take the dot product to find the work done. So work done by gravity, the force due to gravity is mg, and it's in the negative j hat direction. So this is the force due to gravity. So now to calculate this, we simply take this force, we take this negative mg j hat, and dot it with this 4 I hat plus 0.753 j hat meters. Okay, and actually I've sort of mixed symbolic and numerical here, but let's see. So mg, the mass is 220, so 220 times 9.81 is going to be 2158. So this is going to be negative 2158 j hat is our force in newtons, and this is 4 I hat plus 0.753 j hat. Now, taking the dot product here, we just distribute, because you can distribute dot product multiplication over addition. So we do that. I'm trying to make a bigger dot there, but I'm just screwing it up. So j dot I is 0. That's one way to remember it, but the other way to remember it is that we only have a vertical component of force. So really only the vertical change in our height matters. So all that really is going to matter is this negative 2158 times 0.753, our little rise there. So I'm going to take that answer times 0.753, which we had before, and that's going to be 1625 joules, but it's going to be negative. So this is going to actually equal negative 1,625 joules is the work done on the crate by gravity as we lift it up. So negative 1625, but they're asking for kilojoules, so actually I want to do negative 1.625 kilojoules, the work done by the weight of the crate. Okay, and let me just hit enter there, and there we go, and bounce back down. Excellent. Okay, so we got that right. Now, during the crate's displacement, what is the work done by the pull on the crate from the rope? So that's this rope pulling up here, or that way. And I think you can see, it's not terribly hard to see, that if you have, you know, here's your crate hanging down in one position from the rope, and here's your crate hanging down in another position, okay? And say here's one intermediate position. I'm just going to draw so I can show something. Okay, at any given point, the tension of the rope is going to pull, you know, straight toward this point here, but the crate's going to move in a circle about that point. So actually, at every point, the crate's movement is going to be perpendicular to the direction the rope is pulling. So in fact, this dot product, if you take like you're doing the integral of f dot ds, ds is a little vector that points always along the direction you're going, and this dot product with the force, which is always perpendicular to that, this is always going to be 0, because these will always be perpendicular. So the total work done, and you know, even if you don't know calculus, I think it's easy to see that the integral of 0 is probably going to be 0. So the total work done as by the pull of the crate from the rope is going to be 0. And let's see if I'm right about that. And darn, I sure am. Okay. Now, knowing that the crate is motionless before and after its displacement, use the answers to B, C, and D to find the work your force F does on the crate. So, total work done on the crate is 0. Okay. Work done by the weight is this. Work done by the pull from the rope is 0. So, what's the work done by your applied force? So, let me just spell this out for you, which is that, you know, W total. Okay, so all the work done on the crate, this is the sum of all the work done on the crate. It's just the individual works done on the crate by different things. So W due to gravity, which is the work done by the weight, W graph, whatever you want to call it. I'm just saying that's gravity work. Plus W due to tension on the rope, okay, plus work due to your applied force, okay, which I'm going to call W app. Now remember, we showed that total work is 0. We showed that work done by gravity is negative 1.625 kilojoules. Okay, work done by tension on the rope is 0, and so the applied force work is what? Well, it doesn't take much thinking to see that if this all totals up to 0, these three all total up to 0, and this is 0, this has to be positive 1.625 kilojoules. So work done by the applied force is going to be 1.625 kilojoules. And let's see if I got that right, which I sure hope I did. 1.625 kilojoules, and boom, there we go. So that covers you know, A through E. Part F we didn't, you know, we didn't attach any points to, so you didn't really have to solve that. But I'm going to talk about why this is not equal. The answer to A is this sort of this final force you have there. So why is the work of your force not equal to the product of this? You know, this force here and the total horizontal displacement, and the reason is because you don't do this. You're not doing a consistent or a constant horizontal force here. You are starting with very little force. If you've ever had something, even some very heavy object hanging in front of you from a rope, a long rope, I think you've probably found that it is actually very easy to start pushing it a little bit while it's vertical, because while you're doing like a little move back and forth, it's not rising or falling very much. So it's actually very easy to do this. It's only when you get it up to a decent angle that you have to start putting some elbow grease into it to keep pushing this thing. So the force starts out small here and only increases as you move up. So it's not a constant force. That's why you can't just multiply. That's it. So there you go. That's problem 5, and that's the whole assignment.